So I'm happy to be here today. I was actually able to give one of these 5 or 6 years ago, and I really enjoyed it. So I got the re-invite. That must be a good sign. As Alan said, I've recently joined Stanford. Before that, I was at UC Irvine. My background is a little eclectic, which I think this is an interdisciplinary group, so you guys might appreciate. My undergraduate degrees were actually in political science and philosophy. I went to law school and I practiced corporate law in Silicon Valley for a couple of years before going back to grad school at Stanford to study paleoclimate and geology. My PhD was all about the rise of the Rocky Mountains and what happened to the rivers in the American West during that time, which was fun and interesting. And I'm a naturey person, so I like that. But I also realized that's not terribly policy relevant. And I wanted to get back to helping people make better decisions. And so my postdoc years took a turn toward the kind of stuff that I think a lot of you work on. You know, how do we actually reduce our greenhouse gas emissions and get a more sustainable energy and food system? So today, because this is the energy group, I picked a couple of topics that my group's recently been working on that pertain to energy. And as you can see, there are 3 here: aviation, trade risks, and inequalities of air pollution. But I thought I'd take a privilege of just introducing my recent thinking on energy systems research as a whole. So I just have one slide on this. And I think we've come a long way in the past 5 or 10 years towards reaching a consensus, I think, or at least a near consensus, that solar, wind, and electrification of end uses are kind of these core cost-effective approaches to reducing the energy system's greenhouse gas emissions. I think that's more or less settled. There's still work to be done to figure out exactly what that looks like, how fast we go, where the hitches are. But I see really 2 remaining research frontiers that my group at least is trying to push forward on. The first bucket, I would throw in cost-related stuff. So really, I think here it's ever more focus on the difficult parts of that, not just the building solar PV and getting light-duty electric vehicles, but some of the things Professor Jen works on, like the heavier duty transportation or materials and things. And there, I think there's kind of 2 sub-bullets. There's targeted innovation. So, what specific technology costs and performance characteristics are really going to be key to getting a cost-effective net zero emissions energy system. And then more policy-related ones, which is not my wheelhouse, but thinking of how different levels and types of policy interventions can change the outlook for those technologies and costs. The second big frontier that I wanted to highlight are things that I put into a separate bucket that are non-cost considerations. Of course, we can put a dollar sign on anything, so non-cost only goes so far, but these are things like the actual natural resources that are implied in different systems: the land, the water, the raw materials, which we'll get into a little bit today. Issues of political economy, whether that's within a country or among countries in an international context. Social license, how do we actually get and maintain enough social and political support to build out this system? And then all the different co-benefits and trade-offs like air pollution and resilience that we worry about. So today I'm going to have one topic, the aviation, that I think is in this category of difficult stuff. I'll talk about trade risks to energy security, which have to do with the raw materials and the security part of this. And lastly, I'll talk a little bit about work on air quality. So that's my high-level overarching view, and you can tell me later if you buy this or you think that I'm missing something. All right, so as I said, I won't review this, but these are the 3 projects I'll talk about. 2 of them, the first and last, are actually work led by a graduate student that's still at UC Irvine, Conde Bergero. And the middle one's from a postdoc's work, Jing Cheng, who's now at Stanford. So on the aviation topic, what we wanted to do is actually sort of map out the possibility space for getting to an aviation sector that's net zero greenhouse gas emissions. And so, what we started out doing was breaking that into chunks. So one of the ways that we could imagine reducing aviation emissions, of course, is to fly less, or at least shift people's behavior to not use air travel as much. So what you're looking at here in this left panel is, on the left side, the historical trend of passenger and freight aviation, and it's been normalized to, I think that's trillions of ton-kilometer equivalents. And you can see there's a huge dip around the pandemic, but those three lines on the right side are projections of how air travel demand may trend in the future. So the blue line, the industry line, is actually what the various international aviation bodies are projecting air travel demand to be. The business as usual BAU line is more about, okay, if we expect it to go along with projections of GDP, might actually be a little higher. And then the ambitious line is one that we came up with if you really tried to reduce the amount of air travel, for example, by having high-speed rail for terrestrial routes that people wouldn't have to fly, maybe we thought you could get to that low level. The point really is that even at the most ambitious line, we're still going to see an overall increase in demand for aviation, we think. So then that brings us to a second lever that we have to pull, which is, can we use less energy per unit of air travel? So how does the energy intensity of aviation change? And the black line here again is the historical. You can see that the megajoules per ton kilometer have been decreasing over time as we figured out how to make our planes somewhat more efficient and pack more stuff on them. And in the future, various groups project that these things could continue to some degree. So, I think that would help. But of course, we're not going to get to zero emissions from aviation by just being marginally more efficient. We're going to have to do something else. So between those two, we're only going to get so far. And the last one is really going to be switching what kinds of fuels we're using. So of course, the history here is basically a flat line. We've been using fossil-derived jet fuel or kerosene forever. And the carbon-intensive red line is if we just persist in doing that. Those other lines are if we make some progress in substituting for that jet fuel, for example, by electrifying some of the shorter distance flights, and probably more importantly, switching to other forms of liquid fuels like sustainable aviation fuels made with biofuels or even electric fuels. So when I kind of merge all of those into a scenario of what CO2 emissions from aviation might do in the future, you get a lot of uncertainty. There's a lot of transparent overlap in these different future scenarios. But the real point is that the net zero is not going to be reached unless we do a lot of that fuel switching. And of course, this is all predicated on trying to get to net zero in the sector by mid-century, which is really what we would need to be consistent with international targets. So why is the fuel switching so important and so difficult? And maybe this is review for some of you, but really it all boils down to the energy density that we get with liquid fuels. So something like jet fuel has about 45 megajoules per kilogram, a lot of energy. In contrast, anyone know what our laptop batteries are in terms of energy density? Yeah. You had a guess? No? All right, well, it's less than 1 these days. Maybe Alan can correct me. It might be just eking over 1, but it's a lot lower, let's say. And the other part of energy density is not just the gravimetric density, but the volume. In theory, and you've heard people maybe talk about converting airplanes to run on hydrogen. Of course, that's terrific from the standpoint of its mass because it's a gas. So you get 140 megajoules per kilogram, but at atmospheric pressures, it's going to take up a ton of space. So we have to compress it. When you compress it, you have to have pretty robust systems to contain that high pressure gas. And those things weigh a lot. So you kind of cut into your gravimetric advantage. In contrast, something like jet fuel has 3,000 times more energy per volume. So all of this is to say you can do some back of envelope calculations to see on this plot here, you have two of the more popular long-range aircraft, Boeing 777 and the Airbus 380. And the blue bars are showing you how many thousands of kilometers of range those things have using fossil jet fuel. And you can see, compared to that vertical dashed line of the distance between Los Angeles and Beijing, that's why we're able to fly across the Pacific in a go. In contrast, even if we give a plane a big efficiency bonus, if we tried to do that same trip with that same aircraft using hydrogen or batteries, those are the green and red bars, and you can see you're not going to get anywhere near across the Pacific. You're going to have to sort of, skip across, landing on little islands or something if you wanted to try to do this. This is a lot of the reason why we're not going to electrify a huge Boeing 777 anytime soon. So all of that is a backstory to say we got to get a lot of these sustainable aviation fuels. This is a plot then showing if we wanted to do that fuel switching, how much of those fuels we might need in the future. And you can see, of course, again, there are big ranges depending on those other factors of efficiency and overall aviation demand. But you can also see that here in the industry projections, we're reaching a point by the mid-century that we're more than double the total biofuels that we've been using in recent years around the world. Not quite as high as that dashed line at the top, which is all bioenergy, but that's including all the wood that's being harvested unsustainably in the sub-Saharan Africa and everywhere in the world. So the point of this plot is really we need a lot of these sustainable aviation fuels in the future, and biofuels may be a challenge in terms of our other priorities for growing more food, preserving some nature, and not destroying the planet in other ways. So a lot of it comes down to costs. These are two plots showing the cost of different kinds of sustainable aviation fuels. The left one is focused on these biofuels, which the cheapest now are these hydroprocessed esters and fatty acids. You'll see it abbreviated HEFA. And so this plot in particular is showing the vertical axis is the cost of the biomass, and the horizontal axis is the conversion efficiency. And what you can see is one of these, the lower dash line here is actually the current price of jet fuel for comparison. So you can kind of do some comparisons, but in the upper right is kind of the current high-end cost. In some cases, these HEFA fuels can actually be at cost parity with our existing jet fuels, but the real problem is these are actually derived from waste fats and oils, and there's not that much of those things. We don't have anywhere near enough to replace all of the fuels that we use for aviation today. So even though this might be economically affordable, we're not going to be able to scale it to the point that we need. So then we start looking at the right plot, and these are fuels that we could actually synthesize by capturing carbon out of the air, electrolyzing water to make hydrogen, and synthesizing our own jet fuel that when burned would be net zero with the atmosphere. The vertical axis here is the cost of that carbon, and the horizontal is the cost of hydrogen. And you can see that, we're again, down here is the current cost of jet fuel. The current production of e-fuels, at least the ones that have been made, which is still somewhat experimental, way at the top right corner of this. They're very expensive in comparison. So we really need kind of 75% cost decreases in both the electrolysis and the carbon capture in order to reach cost competitive with jet fuels. So all of this is about the CO2 from aviation, but I wanted to spend a second talking about some work that I've been doing in collaboration with a company called Watershed, where I spent some time as their head of science. Watershed is an emissions accounting firm, so they work with a lot of other big companies to try to estimate other companies' carbon footprints and help them decide how to reduce them. This actually, as an experience, was really interesting because it made me get into some of the practical barriers, even things that we think of as cost effective. I started out my talk saying, okay, solar, wind, electrification, great. Some of those things are actually a lot harder when you're at a business trying to invest in solutions. In the case of sustainable aviation fuels, what we realized is that they really represent a really small fraction of current fuels. There's not a lot of data on actually where they're being used, but it turns out there's only a handful of airports that actually have infrastructure in place to handle these fuels. And although you see a lot of marketing from companies like United Airlines, in fact, it's something like 0.1% of their total fuel use that's in this SAF category. Meanwhile, we also learned, or I learned, that the ICAO, this International Civil Aviation Organization, requires that sustainable aviation fuels to be categorized in that category, they only have to be 10% better in terms of their life cycle carbon emissions than regular jet fuel. So while we might throw around that term and think of it as being a net zero fuel, the current standards actually still could be 90% as bad as a fossil jet fuel. And lastly, I'll say there's these international bodies, some of which I'm involved in, like the SBTI, that currently have guidance that disallows what are market-based mechanisms. So the sort of carbon credits that you might trade, or RECs in the context of electricity, these are approaches that allow people to book and claim the environmental attributes. And right now, sustainable aviation fuels are excluded from those things, probably because RECs have had a fraught history of maybe not helping that much, and we're trying to avoid that. But in my view, this is actually hindering uptake of sustainable aviation fuels. So lastly on this topic, I'll show you here the carbon equivalent emissions of aviation in these projections. And what you'll notice here is that in this equivalent, the net zero doesn't actually get to zero. And that's because you can see on the left, the emissions or the climate impacts, I should say, of aviation are not all CO2. In fact, the contrails that are left behind by airplanes actually have a substantial radiative forcing, in some cases nearly half of the total. And so if we actually want to get to a stable climate, we might also need to address not just the CO2 that's coming from burning the jet fuel itself, but these contrails that are formed by aircraft. Some work that I'm doing with a group at Breakthrough Energy Ventures has actually developed a model to look at which flights in particular are forming contrails and how much warming or cooling in some cases a given flight may have. So this is kind of a snapshot from their website. You can see these yellow and orange paths are specific contrails that have formed from flights. The interesting thing about these contrails is they can reflect sunlight back into space and thereby cool the planet, or they can trap outgoing long-wave radiation and warm the planet. And so the question comes, well, how do we know which flights are going to do what, and can we predict that ahead of time? So what we've been doing with Breakthrough is to go through and for a given company, we've looked at all their flights in the year to try to figure out if there's a pattern in which of the flights are having more or less impact. And I'll just kind of fast forward because I don't want to belabor this too much, but the right plot is looking at this particular company's flights over the course of the year, and we've grouped them according to the time of day they were scheduled to depart. And what you see is that the biggest contrail forcing, the red dots that are higher on the plot, are clustered in these evening hours. And that's because, remember I said they could reflect sunlight back to space where they could trap heat? Well, at night, they can only trap heat, right? There's no sun to reflect. So this is a reason if you hate red eyes to stop flying on those things, because they're only ever gonna warm in terms of contrails. Yeah.
A couple slides ago, you said that the radiative forcing from aviation is half the emissions of burning it and half the contrails created. What do the contrails just like act as clouds, or I'm wondering, like, how do you get from how do you translate a meteorological phenomenon into CO2 equivalent when it's not actually a greenhouse gas?
Yeah, so I mean, you've probably heard of global warming potentials. This is our attempt to normalize the radiative effect over a certain time period. So that 90% is actually what a lot of people think contrails as a total of all aviation represent, is being normalized for a forcing that's pretty momentary. It might be on the order of hours, but very large. And they're spreading that out over a 100-year equivalent time period. So that, you know, there are debates about whether that's appropriate, whether we should care more about the long-term forcing of CO2 relative to this short-term effect of the contrails, but that is how at least companies are doing their carbon accounting now. So good question.
Thank you.
All right, so to wrap up this aviation section, I think I made a case for you that, you know, we're going to need a lot of these energy-dense liquid fuels to meet future aviation demands, even if we're very optimistic about, you know, reducing demand and improving the efficiency of airplanes. Right now, biofuels look like they're going to be the most cost-effective path to those energy-dense fuels, but they face a lot of practical and environmental challenges. And then lastly, I made this point that the contrail forcing is also quite large, and there may be issues associated with avoiding those contrails, or opportunities, I guess I should say, where if we can figure out the patterns, for example, flying less over areas where they're prone to form, or at certain times of day where they're unlikely to have any cooling effect, we might be able to drastically reduce those at a pretty good cost. But the residual impacts of those contrails will have to be offset in some way, probably by carbon dioxide. So that's kind of the difficult section of the talk, the aviation. And now we'll kind of probe some of these non-cost factors. So switching gears, I think some of you in the room are well aware that, you know, renewables and electric vehicles require very different materials than do fossil energy systems. So if we look here at the share of materials required by mass on the left, or weighted by Tom Gradle's group's estimate of what's called criticality on the right, we see that these different renewable technologies and EVs on the right have a whole suite of exotic materials that they're using. The point is that that stuff is distributed very differently around the world, which I'll get to in a minute. But I first wanted to say, we have had this analysis where we look to see how much of these materials is on the planet. Do we have enough to actually build all of the solar and wind and vehicles? And the good news that we found was that, yes, there are accessible economic reserves of the materials that we'll need to meet the demand that we project in these different scenarios. In some cases, we will need to ramp up pretty sharply on how much we're producing in terms of annual production. And so expanding the mining operations of some of these things will be required to meet those future demands. But the work I really wanted to talk about today is looking at this distribution question. So here's a couple of simple plots to lay this out. If we think about the set of materials that are required by a fossil energy system to make electricity, so this is the left bar of the left panel, coal and natural gas, this is sort of how global reserves are distributed. You see the US is pretty large in that. Oh, sorry, thought I had an animation. But then on the right is the critical materials we think will be needed for renewable electricity. And you can see that those are very differently distributed. The US has much less, Australia has more, China has more, some of the global south, places like Brazil have more. And it's a similar story on the right. Obviously, transportation from the fossil standpoint is mostly oil, and you can see places like Saudi Arabia really jump out there. On the right bar there, though, we're thinking about some of the materials we need for EV batteries and for the permanent magnets that are in a lot of EVs. And you see that, again, those are distributed very differently. The sort of high level implication from this is, okay, we should be thinking about trade risks as we move toward a system that's going to be based on these different technologies. Should we be worried about who we're trading with and whether we will have access to these materials? So we wanted to investigate this, and there's not, well, I'll tell you how we did it. I'm not sure it's the perfect way to do this analysis. I think what we really need is a tool that doesn't yet exist, but I think it's a good first stab. And what we did was take all of the scenarios from the IPCC AR6 that reached net zero this century. So there's a few, almost 1,100. And we looked at where global resources of these materials exist and how much of the different technologies are used in the year that we reach net zero globally. So these maps are showing you, the rows are the entire energy system, just electricity related technology and just transportation related technology. The left column is if we're trading with our current trading partners only. So there's no change in the different countries that are trading with other countries. The right is allowing some expansion of trade to include all of the countries that have these material resources. And the colors in all the maps are showing a change in a trade risk index that we calculate. And this index is actually derived from something that the energy security community has been using a long time, called the Herfindahl-Hirschman index. It takes into account how much of what you're using is imported, or how much are you depending on imports, and how many sources are there for those imports. So if you have a large share of what you need that's coming from imports, and it's coming from a single trading partner, that's a huge vulnerability, right? Whereas if you've got some redundancy in your supply chain, then of course that gives you some more resilience. So this index is one that we were able to calculate and merge, and what we ended up doing was allocating, weighting the different materials according to not only how much are used in a scenario, but their value. And the reason for this is when we stop and think about a fossil energy system versus a renewable energy system, the materials that you're importing for the fossil system are the fuels themselves. So you need that to operate your vehicle, to drive, you need that oil. That's different than an EV, where yes, you need the materials, but once you have that car, you no longer need to keep feeding those materials as part of the capital, not part of the operating. And so we think we're getting at comparing those apples to oranges a little bit better by assuming that the value is what's really proportional. So that's what I mean by the not perfect approach here. But my overall takeaway is that when you look at these maps, a lot of countries are blue, so they have less trade risks in the future. There are scenarios like here in the electricity, countries in Africa and the Middle East, the global South in general, I would say, that turn red. That's because in many of those cases, those countries are relying on domestic resources and especially oil that they already have for electricity. And so as they are going to be depending increasingly on importing solar and wind materials, they will have an increased trade risk. So in the course of this, we've done a lot of sensitivity analyses to sort of try and assess what the real sensitivities to trade risks are. The top one here is looking at as we add more solar and wind, so scenarios in which there's more solar and wind, which countries have more or less trade risks in those scenarios. And you can see, for example, that the Middle East has more trade risks the more solar and wind is in the scenario. That's again because they're using a lot of their own oil at this point. So if we're phasing that out, that's necessarily meaning they're going to be trading more. But a lot of the regions around the world are actually improving in terms of their energy security and exposure to trade as we add renewables. On the right, of course, if you're trading with more of the countries that have resources, that's going to diminish your risks. So the more we can expand trade networks and have free trade, that will help. The lower panels are looking at how well we're able to recycle the materials. So of course, if you're really successful at recycling EV batteries, that's going to mean you're having to import less. So all of those get lower trade risks as recycling rates improve or increase. And then the same thing on the right. If we're able to actually reduce how much cobalt and lithium and so forth we're using in these batteries, then that's going to make our trade exposure less around the world. Oh, just animating what I said. So finally, I'll show some other key sensitivities here. The way these plots are organized, the left side are the set of countries that are becoming more secure as we move to a net zero system. The right is countries that are less secure. And so if we focus here on this second panel, what we see is that the countries that are getting more secure often have considerable amount of solar and wind. So they're ones in which those technologies are really important. And so that seems to be a factor there. Whereas on the right, the countries that are doing less well seem to have a lot of sensitivity to how many EVs are getting used in their scenarios. So I should have said we're generating these by looking across those 1,100 scenarios and seeing what marginal changes in our estimated trade risks are among the different scenarios that have more or less solar, wind, EVs, and so forth. So the green here in the top right is what I'm looking at when I say the share of EVs seems to make a lot of difference among the losers. The share of solar and wind makes a lot of difference among the winners. If we move down to what materials specifically are involved, it's a similar story. The countries that are kind of getting more secure have a lot of the materials they need for batteries. It's mostly depending on the solar and wind related materials, things that are needed for permanent magnets or for doping EV. And among losers, they don't have the battery materials and they really need reliable access to things like lithium and nickel. And finally, this last panel is just showing, okay, what regions matter most if we are toggling on who you're able to trade with. And the interesting thing to pull out there is it's really important to have trading partners in the global south in these scenarios, which has not always been a priority when we think about the fossil fuels that we're importing right now. It's mostly the Middle East, or it's China, it's India, it's the US. Increasingly, it's places in Latin America and sub-Saharan Africa that have some of these exotic materials and minerals that we'll need. So, yeah, go ahead.
Would you prefer for questions till the end?
I think it's fine. Is that okay?
Yeah, definitely. If you're okay with it.
Yeah, please go ahead.
In that case, could you elaborate a little on what you mean by trade risk? I'm trying to pick it up as you're going along, but I'm not sure I completely understand.
Yeah, so this is what I was saying, that if you have some material that you're going to demand a lot and you don't have that reserve domestically, you're going to be dependent on imports. And if you're dependent on imports, secondly, how many sources of those imports do you have access to? So we've played games where we look around the world to see how many places have lithium deposits. Are you trading with those countries already? Or if we assume some expansion, you would be in the future. And so these are all assumptions that we're making as we iterate our analysis many times. And we're estimating how risky your energy system is to trade based on how dependent on imports you are and how many partners have that resource.
Based on like the consequences of something changing.
Yeah, so a shock would have a disruptive effect on your ability to generate energy and to operate your country.
Thank you.
Does that make sense? Yeah.
In the slide before, you mentioned that like trade partners in like global south, like Latin America, are very important. Like China gets, like countries like China get less important. I was wondering if that also takes into account that like many of the critical minerals in like, for example, Congo or like Chile, I think too, are like actually refined later in China. Like that is, and in the end, it all ends up in China again. So I'm wondering if that is taken.
Were you a reviewer of our paper? No. Yeah, so if I said that China becomes less important, I misspoke, because there are a lot of the rare earth elements, especially, that China has the lion's share of global reserves. So it's going to be important in a lot of these scenarios. What we ended up doing is we got this criticism of, okay, well, where those resources are may not be where they're processed, and that's an important bottleneck in the system. What we ended up thinking was that we, for at least now, could neglect that, because in many cases, the countries that are processing and making the supplies also have domestic resources. So China in particular has a lot of these things. But I think going forward, what we would want is a model that looks at that and looks at the dynamics of how quickly could we actually start processing those things somewhere else. But it's a good question.
Yeah, good question.
Sure.
I guess in the IPCC scenarios, these are talking about the like relative amounts of the technologies, but then I'm thinking for like EVs, the constituent materials may be like dynamic over time, right? Like people are starting to shift away from like cobalt, for example. So I'm curious if you guys incorporate anything like that here.
Yeah, so I did show that in the prior slide, we were looking at these material intensities of energy technologies. What we did was, because you're right, most of the IAMs that generate IPCC scenarios, they might have solar PV, but they certainly don't get down to SIGs and thin film and other things like that. So we took sort of a recent snapshot of the distribution of those different types of technologies, and we rolled that tape forward in our assumptions. But then we had these sensitivity tests where we dialed back how much cobalt, how much lithium, and so forth you needed per unit of capacity, and try to test the sensitivities. But yeah, it was a huge data exercise to do that. And who knows if we're guessing right or pulling out the interesting results as we should. Okay, so yeah, I guess to wrap up the section on trade risks, I think the main takeaway here is that everyone talks about the concerns that we may have being dependent on critical materials for the future of our energy system. What we were interested in doing was trying our best to compare the apples to oranges of, yes, but we're also not going to be importing as many fossil fuels. And that's had a really difficult history of price volatility and global conflict associated with it. So we wanted to at least see how those balance out. And I think the takeaway is that even if you don't worry at all about the fact that one of these things is going to be more disruptive because it's needed to operate your infrastructure, that's the fossil fuels, versus ones that are just being used to build the new technologies. Even if you ignore that distinction, we expect that trade risks in the future are going to go down under a net zero system. And I think that's a message that policymakers deserve. All right, so the last part of the talk is looking at what happens to air pollution under net zero emission scenarios. And this actually came out of some ideas that originated in the National Climate Assessment, which Professor Jen was involved in, same chapter as me. And in the course of that, we had some experts on our team that were focused on environmental justice. And we were using this term net zero, and several of them were sort of objecting. And I didn't really understand why. I thought, it's a climate friendly future. That's what we're all aiming for. But once I started digging in, I realized what they were worried about. And that's led to this study that I'll explain. So what you're looking at here are 3 scenarios in the rows. The top being sort of a business as usual reference scenario for the US energy system. The middle being a net zero scenario that reaches net zero by mid-century with a lot of carbon dioxide removal. And the bottom row is one that reached net zero mid-century but has much, much less carbon dioxide removal. We actually tried to get it as low as we could, couldn't get to zero. The columns are looking at, on the left, what energy technologies are being deployed in those different scenarios. The middle is the greenhouse gas emissions. So you can see in the bottom 2 panels here that the net zero is achieved with some amount of carbon dioxide removal, the green below the zero line. And on the right, we're looking at the PM 2.5 emissions related to the different scenarios. So a couple things to note here, the PM does go down dramatically in the net zero scenarios, but it goes down less in the low CDR scenario. The reason for that is that if you have more carbon dioxide removal at net zero, that permits you to have more residual emissions in those scenarios. And the residual emissions aren't just greenhouse gas emissions, they're co-emitted with PM 2.5 pollution. So it's not like the CDR is actually causing this PM 2.5 emissions, but it's allowing the extension of life of infrastructure that is producing that pollution. So when we look at then where that PM is likely to be emitted, we downscale according to the current locations of infrastructure, and we do some assuming of where things will retire in the future according to their age and cost effectiveness. What you get is these maps of PM 2.5 concentrations in the year of net zero on the left. You can see that both of the net zero scenarios are far less red, so they have less PM 2.5 pollution than the reference case at the top. But there is also a substantial amount more when you have that high CDR. We then fed these results into an epidemiological model, the BenMap model produced by the EPA, to look at what sort of projections of mortality and morbidity are associated with it. So these are annual deaths in these different scenarios in the year of net zero. And again, you see there's a substantial drop off in the net zero scenarios, but there is a meaningful distinction in those 2 different CDR cases. So the last thing we did was we actually zoomed down and we ran a pretty sophisticated chemical transport model at a 1 kilometer scale over 15 of the most populous cities. Now, the point of doing this exercise to get to that level of granularity is because we wanted to start looking at community level differences in these air pollution impacts. So these are just taking a couple cities that you all are probably more familiar with. And I think the main point here is you can see that the levels of impacts, these are avoided deaths in the low CDR scenario relative to the high CDR scenario. So the difference just in the 2 net zero scenarios are spatially heterogeneous. They're not just broad over this area. They tend to follow highways and be clustered around point sources. So as others have found, if we actually then take the step of looking at, okay, who lives in those different pixels within the city, you can see that places with lower income or less white communities tend to have a disproportionate number of these deaths from air pollution in those scenarios. And that's what's being shown by these bars. So as you move from left to right, you're going to lower income neighborhoods, or left to right in the right panel here is less white areas. And you see there is a meaningful increase in the amount of excess deaths relative to the mean. The last step though, and this is the key, the linchpin for this study, was to look at, does the low versus the CDR have more of this disproportionate impact on vulnerable communities? So the way we try to depict this is, I'll take a minute to explain. So the horizontal axis here is looking at the deaths in areas that have less than 30% whites living there versus on the vertical axis, it's deaths in areas with greater than 60% whites. Meaning that if you are right of that dashed line, you're in an area where there's more deaths happening in less white areas. The different cities plotted on here have two circles. The filled circle is in the low CDR scenario. The hollow circle is in the high CDR scenario. And the thing that I'm really wanting you to pick up on is that the slope of these lines that connect those two scenarios is not parallel to the line of equality. What that means is that as we move to a scenario with high CDR, we actually have a disproportionate impact on these vulnerable communities. And I think this really boils down to the fact that where we have infrastructure located today is disproportionately impacting these communities. And as you have more CDR, then you allow those things to persist. So the sort of takeaway of this is, this is all why environmental justice groups are skeptical of the term net zero and carbon dioxide removal technologies in particular. It's not unfounded. That skepticism is really borne out by the analysis. And I think, the antidote for this is to be more intentional about how we retire infrastructure and take into consideration these justice implications and not just do the easiest, that thing of retiring the oldest thing, the dirtiest thing first, but think about exactly who's being affected by the different sources of pollution in the scenarios. So that's what I had for you today, and hopefully I left enough time for a few questions. Thanks, everyone.
Question,
Please.
I hear a lot about, there a lot of skepticism about like totally, electrifying like air travel, or people are saying like we're never going to get all air travel on hydrogen or on electricity. Do you think that there's too much of like letting perfection be the what would they say, the enemy of progress? Right? Like, do you think people should be a little bit more focused on like making a little bit of change where we can?
Well, I mean, to start, I would agree that we're not going to electrify all air travel. Hopefully I made that case at least a little bit to you. Do I think we shouldn't try to electrify any? No. I think, if there are short flights, if it's LA to San Francisco and someone wants to build a business to do that, I'd say power to them. That's likely to be a good approach to reduce emissions. I'm not sure, maybe this is something you guys could research, if high-speed rail would be a better option, but of course, we can talk about the benefits of high-speed rail without getting bogged down in political realities that we haven't been successful in building. I don't know if that answers your question. I think we should make incremental progress, I guess is what I'm saying. Especially in the current political moment, it seems to me we're going to have to satisfy ourselves with incremental progress.
whatever.
Yeah.
I have a maybe less interesting one, but I just wanted to, scroll back or?
Yeah, sure. How many?
Skip back, maybe like 1,000.
Listen, yeah.
What are the percentages on the top of the bars?
That's just showing the median value that are associated with those bars. So it's the white lines in the bars.
Oh, I see.
Yeah.
Okay.
Just meant to, it's hard to eyeball the exact figures, but it's nice to have at least one.
Oh, I
number
see,
on
I
it.
get it now, yeah, okay, never mind, yeah, that was it, sure, yeah.
So I should do better about explaining everything that I put up. I think sometimes I try to pack too much into these.
A more technical question. So I was surprised by this because I always thought that carbon removal system need to clean the air first because of like the long-term stability of the carbon sequestration plant. So I always understood that they actually clean the air pollution before getting the CO2 out.
I think you're not wrong about that, but what you might be missing is that in some of these cases, the ways that we're actually removing carbon are completely decoupled from the source of emissions. So it's not CCS mounted on a point source. It's we planted some trees that are balancing the power plant that we still have operating. And so in that case, of course, it doesn't get the PM.
So it becomes kind of we are reducing carbon emissions, but we're allowing these to continue to operate. It's kind of
at least in these particular scenarios, which I should have said, these are coming from the GCAM USA model, which has its own biases and maybe will do different things in reality, but assuming that this model was right, then there's still these PM emissions happening. Other questions? In the back.
Are the low and high CDR scenarios influenced by a assumed carbon price that's driving low and high CDR, or is that like, did you decouple that from this analysis and just let that, assuming we're, removing carbon and assuming we're not?
Yeah. The way that we set up these particular scenarios was we obligated the net zero goal by mid-century, but then we got low CDR by turning up the cost of the CDR technologies artificially in the model to sort of disincentivize their use.
Okay.
But if you turn them up too high, the model blows up and can't even solve. So
Yeah.
that's why I said it's low, not, we wanted to do zero CDR. Oh, what happens if you have none? But
Yeah.
couldn't do it. So,
Okay.
yeah, sorry, yeah, go ahead.
Yeah, so just a simple question. So when you evaluate the trade between different countries, right? What kind of indicators do you use to evaluate the trade between different countries? I'm just curious about that.
What do you mean by indicators?
Such as like, for example, in the electrical vehicles, right? How many EVs are you import or export, something like this?
So yeah, what we looked at was a little simpler than that. It was just, for a given amount of electrification, what sort of level of demand of a given material would we expect based on the current material intensity of electric vehicles? And then among the trading partners that you're interacting with in our assumed scenario, do they have sufficient material reserves that they could supply to you? And we did, I didn't get into this, but there are backstops where you might be trading with 3 countries now, but 2 of them have very small amounts of those resources that we would expect to be more or less depleted before you reached 2050. And so there was a sort of a constraint based on the amount that different countries have. But there wasn't a lot more detail or sophistication about how many vehicles or things like that. Yeah.
Could you explain that criticality you were talking about with the materials?
Yeah, so I don't know how many of you are familiar with Tom Gradle. He's an emeritus professor at Yale. He's like one of the early progenitors of this subfield called industrial ecology. You may have heard of. Anyway, his group in maybe the early aughts had some papers in PNAS where they introduced what's called criticality. And what they're looking at there is several different things, really. One is just, how much of this resource is available, so along the lines of the index that we've calculated. But the other one is how substitutable the different materials are in their function. So there are some specific, electrochemical functions that materials can perform that have no substitutes. So, and I can't give you a great example. I should go back and read his papers, but there's some materials elements usually that just are sort of uniquely capable of doing certain tasks. And there are others that there is some flexibility. You might be able to use one that has slightly less efficiency, but it'll still get the job done. So their metric of criticality takes all that on board and tries to get at how vital is a particular material to the technology we're trying to use it for. It's a pretty cool analysis if you haven't read it. Yeah.
So I see in that in subplot D there,
Yeah.
like in the high CDR, there's just more energy demand. And it looks like it's mostly in the form of what, biomass? Oh, I see, and oil as well. So you're saying in the model that when you have more CDR, people are more likely to use fossil sources, but also are just more likely to use more energy? Is that what you're saying as well? In this model?
They're definitely more likely to use things that emit. So the biomass you mentioned is one that in some cases is going to be associated with PM 2.5, but there's also more ongoing use of oil and gas in that scenario.
Is there efficiency in here? Is that why it's maybe lower with the low CDR?
Yeah, I think that's exactly right. So, there is sort of a tax if you're using some of this energy to remove from the atmosphere. I think that's probably part of what's happening.
And I guess you can kind of like justify the high CDR saying like, oh, well, if people are more willing to use fossil sources and they're also renewables and people are just more like needing more energy and that's why people are using more energy in that scenario. Like overall.
Yeah, I mean, I think that's fair. I think one thing to say is that in these residual emissions, industry becomes really important. We do successfully electrify a lot of the transportation in both of those. The things that stick around if you have access to CDR are heavy industries, which are more expensive and difficult to decarbonize on their own. So we prefer to just do CDR. So that's a lot of the difference.
Interesting.
Yes.
You said this paper is not yet published?
The aviation paper is out, but the other two are in review right now.
So, yeah, question for the second study for the trade. It's my understanding you're measuring trade risk using the HH index, the Hirschman.
Yeah, HHI, right.
So that's like an index that measures market concentration. And one could ask, like the question is the same like having 20% of your supply coming from a friendly country versus a more unstable country?
And we thought about this. We thought of a couple ideas. One would be somehow weighting according to the stability of the trading
US
partner.
perspective, you know. Right?
Yeah, exactly. Well, so that was the thing we ended up deciding to not get into this because it really matters which country you're in, right? One world looks great to China and terrible to the US. So, but yeah, we thought another possibility would be to somehow incorporate just some metric of political stability. Especially because, as I mentioned, a lot of these resources are in the global south. Some of those places aren't always that stable. And so that could be another risk to bring into a subsequent analysis. But yeah, we didn't actually pick and choose. We did sort of a random expansion or contraction of the trading partners. Probably is a straightforward enough thing to do something more specific to the US interest, for example, but that's not what we did.
Sorry, I wasn't paying attention.
Are we over time?
No, for the folks online, I think there was a question.
Okay.
Fran, did you raise your hand?
Oh, no.
Yeah, can you hear me okay?
Yeah.
Hi, Steve. I have a question about the sustainable aviation fuels. As you kind of noted, like, there's been this longstanding challenge with ethanol that, we get this induced land use change, both internationally and domestically, that either certainly partially, if not fully, offsets the kind of carbon benefits from it. And I'm wondering, does that come into the accounting that you're doing in that study, or in kind of what companies are doing when they're thinking about like doing their, say, corporate emissions accounting, like through Watershed and so on?
Yeah, it's a good question, of course. I wouldn't expect anything less, Professor Moore. But right now, our study didn't really get into that. We just said, okay, we're going to need net zero fuels of this amount. And in theory, they could be biofuels or electric fuels. But if they are biofuels, we got a long way to go to make them truly net zero, is what you're pointing out. As far as the corporate accounting, you won't be shocked to learn that most of the corporate accounting standards allow all biofuels to be regarded as net zero, or so they just give them a pass. And that, really needs to be revisited. The greenhouse gas protocol right now is under revision. And so I would hope that that's part of the conversations that they're having.
Yeah, I guess I hadn't realized it was, quite that bad. I didn't realize they would just count it as zero. Like not even like process emissions from agriculture.
I mean, if they're including any of that, they're doing an incredibly diligent job. There's a lot of flexibility in those standards because they're not, law, they're voluntary standards. And so they do have stuff about, well, you could track biogenic emissions on a separate set of books and things, but in practice, I don't think very many companies are doing it.
Okay.
Any other questions?
Hi, I'm curious when you look at trade, at that scenario, if you're incorporating at all kind of the nature of the trade, is obviously kind of you're accounting all trade as kind of equal from what I can see in the graphs. But obviously, I mean, you mentioned Congo earlier, there's a lot of kind of coercive mechanisms there, internal corruption. That means that the nature, political nature of the trade is really different depending on where it is. So I'm wondering if you looked at how there might be some kind of, incentive for more kind of imperial expansion for this rather than just like more free trade.
Yeah, so this particular analysis is super high level, and I think you're pointing out a whole set of really fascinating research topics to dig deeper. I think we just wanted to kind of get this high level message that trade risks go down under net zero, so let's not be afraid of pushing forward on decarbonizing. But I think you're raising some things that we're following up now, which is, not all resources around the world are equal in terms of their social and political and environmental impact of extracting those resources. And so I think we want to start doing some more analysis of those things and trying to get at what does the supply curve look like if you prioritize some of these other issues. But I think that's a hot topic that if you guys are interested, we should talk.
I'm not sure if your aviation study looks into this, but how do the techno-economics compare between biofuels, ignoring all the supply constraints for the infrastructure, e-fuels and demand substitution through high-speed rail? Because we've seen in the case of San Francisco to Los Angeles high-speed rail that the capital constraint is real. The initial estimates were not what the actual cost of the high-speed rail was. How do these three stack up? I saw the graphics for biofuels versus e-fuels, but not the demand substitution for high-speed rail. How does it compare?
Yeah, no, it's a good question. Our analysis is, again, pretty high level, so we're leaving a lot of these details aside to be figured out. But in practice, doing any of those things is going to have its own set of constraints, cost of capital being a big one, especially in the context of international development, right? Costs of capital is much higher in some of the global south than it is here. But yeah, we didn't really get into that. I think it's a good topic.
A little bit of a follow-up there. We see that the oil companies are investing in research and development around carbon capture and sequestration. What is the silver bullet that aviation industry is investing on in terms of R&D? What do they expect to be the savior?
That sustainable aviation fuel. There's that's what they're hanging their hat on. They need to have that in order to make a claim that they're not destroying the climate. And that's why I showed you United's Oscar the Grouch is their new spokesperson, right? So they're thinking that that's the ticket forward. And I think there's some potential there, but it's also like renewable energy certificates and other investment vehicles. There's a lot of opportunities for it to go awry. So those of us in the room need to keep them honest by doing studies to show what the real benefits are and setting the standards appropriately.
So I was wondering if maybe back out a little bit and think about sort of broader picture. I mean, you're answering and investigating these like big sort of important questions, and I wonder if you could give some motivation of some kind to our students here. I guess don't totally mean to be putting you on the spot here, but like, how is your vision for answering some of these questions maybe changing over this last week?
Well, I think some of the macroeconomic trends, and I said this the last time we had the Trump administration, are not going away. I think the real decrease in costs of solar and wind and EVs is not disappearing here. I think there'll be new headwinds, of course, but I'm optimistic that at least the direction of travel will stay the same, if not the rate. So as far as my research, though, I think some of the issues that I made a case for in that first slide, I think are very much on the table. It's like, what does it look like as we push forward? Whether there's a strong policy tailwind or not, I still think we need to be thinking about issues like air pollution and national security and so forth. So, personally, the way I approach research, I don't know if this will be interesting to you all, is I think of the questions first. So typically, I don't know what data I'll use, what model I'll use, who I'll collaborate with or anything. It's more about what is the question that I think is scientifically interesting and policy relevant, and I think it would be fun to look at. And then I go after that, and sometimes that means like working with folks like Professor Chen or Professor Miller in the back, and tackling those things. But I hop around a lot, like you saw in the talk, so I'm not like someone who's easy to pigeonhole on a topic, and this is just energy stuff I'm working on. I have others in the food sector, impact stuff. But it keeps it interesting, and I think that's why I love academia. And hopefully my job won't go away in the next.
I think you're safe in California.
Yeah.
Hopefully. Yeah. All right, so.
Well, thanks for having me. I appreciate it.